Okay, you guys can hear me? Nod your head. Okay, can you hear me all right? Yes? Okay. I will share my screen. Thanks everybody for coming. Excellent. Thank you for the invitation to come here. Let's maybe let me leave Gmail up. So if you have any questions or anything, just go ahead and text me in this box over here, and I can take them. So we're going to talk about predictive modeling. I had some slides that I put up earlier today. So if you go, I wrote a book a while back called Applied Predictive Modeling. So if you go to the website there it's appliedpredictivemodeling.com, like one word.com, and then there's a blog post that today has a link for the slides and the code. So all of the things I'm going to show today, the data is in one of the R packages, so you can reproduce everything that I'm going to talk about. Excellent. All right, so we'll go to full screen for a few minutes, and then I'll check back every once in a while to see if there's questions. So I guess, maybe before talking about how we do some things in R, maybe talk about what predictive modeling is. I have kind of a loose interpretation of that. So when you think about machine learning or data mining or pattern recognition, a lot of times what you find is people have, over the years, sometimes it changes, but they have specific methodologies that they're thinking of when they talk about those particular techniques. So it used to be that when you talked about machine learning, it was all about neural networks. And then with the rise of support vector machines, I think people at that point thought, well, you're talking about kernel methods at that point, whereas now when I hear people talk about machine learning, very often they're talking about network models. So those things are not very descriptive in terms of what the models do, and so I kind of prefer the term predictive modeling because we're talking about prediction, and that's not terribly specific, so I'll elaborate a little bit. So really, I don't want to say, hey, model X is a predictive model and model Y is not. Basically, I'm thinking about any models where really your focus is on prediction, and that might seem kind of obvious. Why wouldn't we be focused on prediction? But at least when I was in school and in university, the focus very often was not on really prediction for models. It was about interpretability, or more often than not, inference. So when we talked about linear regression, we focused on things like the p-values and ANOVA tables and things like that. We weren't ever really all that focused on what the predicted values were. And so when I talk about a predictive model, I mean any model whose primary goal is to achieve the highest level of accuracy possible. It doesn't mean you don't care about interpretation or inference, but those are really secondary concerns compared to the prediction part. So you could say, well, anything could be a predictive model, and I guess that's basically true. But again, the thing I'll emphasize is really the quality of the prediction is really the focus. And again, when we can make inferential statements, we will, but that's really sort of an added bonus to what our primary goal is. So here's some examples of times where you might not really care about interpreting the model. So for example, spam detection is the classic example I use to non-technical people when they ask me kind of what I do for a living. You don't really care necessarily why a message was spam. You just really want it to be accurate. You want it to catch the spam so you don't have to see it. But more importantly, you don't want to have many false positives, so you miss that email or SMS message from your boss, your girlfriend, or whatever. So really, what you care about there is accuracy, not necessarily whether it was a Nigerian prince or Viagra or whatever the reason was it flagged as spam. Same thing about like plane delays. You might want to get a prediction whether your plane's going to be on time or not when you're at the airport. You don't necessarily care why it is, whether it's inclement weather or anything else. You just want to know as accurately as you could. Sentiment analysis is another good example. When you're reading text, you want to get predictions on whether somebody has a positive or negative feeling about something. And in that case, you kind of do care why they feel that way. But very often there's an inverse relationship in a lot of these models between interpretability of the model and performance. So you're better off reading the actual text than having the model tell you why something is a positive review, let's say, or a negative review. Another thing is the sale price of a property. So, I sold a house last year, and I kind of want to know why or what things I could do to make my house sell for a higher price, but the model's going to not necessarily be as good at telling me that as a local realtor would be. So, when I'm looking and want to make predictions, I want to get a really good assessment as to why, or, not why, but how accurate I can predict the sale price of a house. And so, again, the focus there would be on prediction. Another example that we use a lot at my job. So I work at a pharmaceutical company at Pfizer. I'm in drug discovery. So I'm in early part of drug discovery where we're developing the actual molecules. And one of the things that we do is this stuff called QSAR, which is quantitative structure activity relationships. And so what happens is we synthesize a variety of different molecules, and we can take those molecules and they have chemical formula, and then we can derive a lot of 2- and 3-dimensional and other sort of descriptors of molecules. So if you give me a chemical formula for a compound, I can tell you how heavy it is, its surface area, and all sorts of things like that. And we have, millions of compounds like that. And so for a lot of these compounds, we screen them in laboratory tests called assays. And from those assays, we can detect, or we can predict, what the assays measure really is whether something is potent. So whether it's hitting the target that we want it to hit, whether it's toxic or safe. We have assays for whether something's permeable or how greasy it is and that sort of thing. And so when you work with chemists and they are synthesizing, or before they synthesize a new molecule, they may write down a chemical formula and say, hey, what happens if I add a fluorine to this? And before they synthesize that, we can run it through a lot of these model predictions and tell them, oh, well, that thing was cleared very fast out of the system once you add that fluorine in. And we can get quantitative measurements on that before they ever actually make the compound. And again, that's a situation, if you talk to the chemists, they find QSAR models, at least the chemists I work with, tend to find QSAR models extremely helpful in terms of understanding how they should design their molecules. But they don't necessarily want the model to tell them why the prediction was the way it was. They'd actually kind of be a little bit insulted if they felt like the model could tell them more about chemistry than they knew. So again, this is another situation where really prediction accuracy is very important. We have some models that we use a lot, and if I can increase the accuracy of that model by 5%, they'd probably throw a parade. So accuracy is really critically important to them. I just want to check you guys can. I'm assuming since I don't have any messages, you guys can hear me okay and see everything okay. So I'll check back in every few slides. All right, so I'm going to talk about some data in a few minutes, and I thought I'd maybe preface that with a picture. So here are pictures of some cells, and so on the left-hand side we have some fibroblasts, and in the green there is really, we stain these cells with a couple of different colors, stains, and those stains can basically highlight different portions of the cells when we take pictures of them. So in this particular instance, the green is highlighting a part of the cell that's in the cytoplasm. And so when you look at the green there, that's really demonstrating where the cell body is. And then the part that's stained the blue is staining something that is, I think it's staining RNA. So it's basically measuring where the nucleus is. So when you see something that's blue, you know that's where the nucleus is. You see something that's green, you know there's part of the cell body there. And so what we can do is we can do cell segmentation algorithms. And what those, you can see the results of those on the right. What the segmentation algorithms do is they try to highlight where the cell or nuclear boundaries are. So on the right, you can see the same cells in a black and white image, and then the yellow sort of contours around those are things where we say, okay, there's an actual cell here. So when you look at this one kind of in the middle, it's a little bit granular, but we would say, our segmentation algorithm would say, hey, the pixels inside this part of the image are from the same cell, and then the blue here says, hey, the pixels inside of this circular boundary is the nucleus. There's some red things here, and they're not really material for this particular part of the talk. We're staining a third stain to find a particular organelle that's in the cell. But I just wanted to take this to demonstrate that we can take these images of cells and then try to find where the different parts of the cell are on the image. And then what the goal here would be is we want to quantify different aspects of these cells. So for example, we might want to change where a certain protein is in the cell. So if we have a control compound that doesn't really do anything, and we treat these cells with it, we wouldn't really see any change. But let's say we knew that a protein, we wanted to see where that protein was in the cell body. Let's say it's in the cytoplasm, and we want it to go into the nucleus. And so what we would do is we would treat other cells with a particular compound that's not a control, and then we could take the cell body and quantify where the actual protein is. So what we can do is we can quantify the difference between the control cells and the treated cells and measure different aspects of them, like how big the cell is, what's the intensity inside the cell of a certain color. So if you see more intensity outside the nucleus than inside the nucleus, you feel like, well, the protein didn't really get in the nucleus. But if the converse were true, you would see kind of dark outside of this blue circle, but light inside of it. So while we're developing drugs, there's a lot of different things that we want to quantify about these cells. But we can't really do that until we've segmented them, until we know what pixels correspond to what cells. And so the example that I have is a situation where, and this is pretty typical, where we have some sort of conflicts, where you can see there's a cell down here and it's kind of next to this other cell, and you can see what the segmentation algorithm does. It kind of draws a little wall in between these things. And I'd say it did a pretty good job down here, that this particular area is portraying the area of this particular cell fairly well. It's not really having a problem with this cell. But when you come and look up here, there's three that are kind of next to each other. And this is probably one contiguous cell here, but the segmentation algorithm kind of messed up here, and it thinks, you know, this is one part of the cell. This guy here, it's kind of an island with another island sort of next to it, connected. It thinks that area is one cell. And then you have this third one over here that, you know, this area right here is probably one part, and it's pulling off another part of the cell that's in the middle. So these would be well segmented down here when we think they're doing what they should do. And then these ones up here are really poorly segmented because we didn't really get the boundaries of the cell right. And that's kind of a big deal for us, because it really, once we start quantifying these cells that are poorly segmented, we can't really say, or it's almost like data contamination, that the things that we're measuring inside these cells aren't necessarily accurate because we haven't used the right pixels to designate where a particular cell is. So I'm going to talk about some data that's in our package. And what they did is they actually looked at a lot of cells and classified them as being well segmented or poorly segmented. And then they have all these measurements of the cells, like, you know, how big they are, how bright they are, whether they're very flat, like thin sort of pancakes, or whether they're more round. So they have all these descriptors of the cells. And what they want to do is they want to take the descriptors of the cells and predict whether they're well segmented or poorly segmented based on the visual measurements that people have made on those particular cells. Okay, so let me turn back here. Okay, good. All right, so what we want to do is we want to take the cell segmentation data and predict which ones are poorly segmented. So we have individual cells. Those are like the rows of the matrix. And then we have measurements of, like I said, their size or shape and things like that. And those are the columns in the matrix. And so what we want to do is we want to take, again, the characteristics of the cell and predict whether they have been segmented properly. The reference here is Hill in 2007. The data is at the is on the website. The sort of classes of the data, so when they looked at them, they classified them as either poorly segmented, which is designated as PS, or well segmented, which is designated as WS. And they had 58 different measurements on the cells that we can use as predictors. And so if you want to get at these data, they're in the carrot package, which we'll talk more about. And then you would say data, it's called segmentation data, and that will load it into your workspace. If you look at the dimensions of that data frame, there's 61 columns, and there's about 2,000 cells that have been measured. And if we look at the first, let's say, 9 columns, the first column is the cell. It's like a cell identifier. The second one is, we'll talk a little bit about this in a minute, a training and test set designator. So they have a column in here that says what data set it should belong to. And then the third column here is the actual classes. And that's a factor. The first level is poorly segmented. The second level is well segmented. You can see that the first row in that data set is a 1 here, which means it's poorly segmented. And you see a bunch of different predictors. So channel 1, the CH1 here, indicates something that measures the cell body. So when you look at the area of channel 1, that's basically the number of pixels that are inside the entire cell body. If you see area channel 2, channel 2 in this case is for the nucleus, you would get a measurement of how big the nucleus is. And then they have things about the average pixel intensity of the cell body, the average pixel intensity of the nucleus, and so on. So again, I've shown you, let's see, 6 predictors here. There's actually 58 in total that we'll use to then again try to predict this column here for poorly segmented and well segmented. Okay. I can take a minute and answer any questions. All right, we'll go ahead and type them in if you need to. So when you go to do predictive modeling, there's really a few different steps that you might want to take. One is the thing that we think about the most, which is estimating model parameters. So for example, if you're fitting a linear regression, you want to take some data and estimate the slopes and intercepts and things like that. I'll talk about what a tuning parameter is, but another activity you might need to do is to change some of the structural parameters of your model. And that's something you're going to want to use data to make decisions on, and I'll go into a lot of depth in that in just a minute. And then, a third thing you might want to do is characterize how well your model is doing. So, you fit a linear regression, you kind of want to know what the R-squared is. Should I use it? Should I not use it? Maybe compare that to a different model and so on. So there's a bunch of steps that we would typically undertake. And then we have a finite amount of data to do that with. So in our segmentation data, we have a little bit over 2,000 cells that we've labeled as being poorly or well segmented. And so what's typical people do is they'll split their data into 2 or maybe even more groups. But I'll just focus on 2 right now. And the first one they would call their training set is a data set that they're going to use to actually fit their models, estimate their parameters, and maybe compare models, a lot of different models. So it's sort of your playground. You want to try out a different pre-processing method, or maybe you want to try random forest instead of logistic regression. You're going to use your training set to do that. So that's kind of the area where you experiment with. And then there's a test set. Some people will call it a validation set, depending on the era that they started doing this. But that's really a set of data that's reserved to get an independent assessment of how well the model works. So what you don't want to do is you don't want to keep fitting dozens and dozens of models and using the same test set to evaluate performance, because if you do that, then what you're doing is you're using the test set as part of the training process. And so what you typically do is you wait till you have 1 or 2 candidate models that you feel really good about, and then you would evaluate them on the test set as sort of like a bake-off to get a final choice between models. So there's always this question about if we're going to split our data into 2, how should we do that? So if we spend a lot of our data on the training set, then we think we'll be getting much better parameter estimates, but then again we might not get very precise measures of model performance. But the converse, if we dump a bunch of data into testing, then we are not doing as good of a job estimating our parameters as we could. And so it's really an art to doing that. There's no tried and true percentage that you put in one or the other. And to be honest with you, if you have a ton of data, it doesn't really matter all that much. The times when it matters is when you have a moderate to a small amount of data. And another situation that it would matter a lot would be when you have a big class imbalance. And what I mean by that is you have one class is a very rare event. In that case, if you have a 5% event rate, you kind of want to make your test set big enough to where you can get an acceptable level of performance on those particular events you're interested in. So there's kind of an art to picking what your training and test set should be. A lot of statisticians would say that you should put all of your data into training because that's where you get the most benefit, that you're wasting your data by putting them in a test set. And I think from the statistical perspective that's fairly true. The downside is it's easy to get sort of led down the wrong path by doing that. We'll talk about resampling in a few minutes, and there are situations where you can do resampling poorly, and get biased assessments of how well your models are doing. So at least in the environment I work in, even if the test set is very small, we tend to almost always have a test set just to double check things at the end. As much as I can, I get the scientists or the clinicians or the people I work with to blind me to the test set. So there's no chance of me being biased by what the results are. They'll typically give me the samples without their labels. I'll predict them, and then they'll tell me how well I did. That's a fairly standard way of doing it. So, you know, you ask a statistician any question, and the answer is it depends. And that's basically the answer here. For this particular data set, the authors classified about half of the data into testing and about half into training. And I wouldn't normally do that. I wouldn't put that much into testing. But I'll just kind of follow their lead here, and we'll use the same test and training set that they had. So now that we've loaded the data into our working environment, what I'll do is the first thing I'll do is I'll get rid of the cell identifier because we're not really going to use it anywhere. And then I'm going to subset the data from the original data. I'm going to call something called seg_train, and those are the cases that originally were in the training set. And then the ones with the test set have this designation. We'll put them in a separate data frame, and then we'll get rid of the case because we don't really use it after this anymore. So I'm saying in all those columns, it's the same thing as getting rid of those columns from a data frame. So I'm going to do all my modeling and everything on the training set, and then I think maybe once or twice in the notes I'll do analysis on the test set. And it's probably not how I'd normally do it in practice, but just for illustration, I'll be using the test set to show you how to compute some things. Now, let's say you didn't want to do a 50-50 split, or let's say you want to do a 50-50 split and didn't want to use what the authors use. How would you do that? So the carrot package has a function called PreData Partition, and what that'll do is it'll take a stratified random sample of your data based on some factor. And so it takes a stratified random sample, again, because if you have a 5% event rate, you kind of want to make sure the event rates in your training and test set are proportional to what the original data were. There's a lot more to say about that, why you would want to do that, but that's what this function does. So you give it, from the original data set, you can give it the factor that is poorly segmented or well segmented, tell it what proportion of the data to select, so 50% here, and then I don't, normally it'll give you the results back in a list, and I don't want it to give me that back. But when I run this function, I get this object called inTrain, and what that is, it's a bunch of integers. So if it was the first couple values are 1 and 17 and 300, that would say that the subset that you randomly selected, those rows would be included in the subset. So if I want to put 50% in the training set, those integers I would use to subset the original data and keep all the columns, and that's what my training data would be. And then in R, if you use negative integers in the rows, it gets rid of those, so this is what my test set would be. So again, I'm going to use the original split that the authors used, but in case you want to do something differently, you can do that using the code that's here. And again, this is in Caret, which we previously loaded, so it should be available to you. Okay, I haven't seen any messages, so I'm just going to keep going. So probably the biggest thing to watch out for in doing any machine learning or predictive modeling is really overfitting. Overfitting is really where you find some trends and patterns in your training set, and your model picks up on those and tries to capitalize on them. But if those patterns aren't really there in other data sets, then your model works really well in your training set, but would really do poorly on your test set or any new samples that you want to predict. And so that's really the fear, is that you have a model that works right now for the data that you have, but it won't work in the future. And that's a problem for some models and not for others necessarily. And what happens is a lot of these models have tuning parameters. And so these are parameters that are usually structural parts of the model. They're parameters that can't be analytically estimated. So for the most part, there's no equation that says, oh, the tuning parameter value should be 7.8 or anything like that. So we'll talk about, I'll illustrate a nearest neighbor model in a minute, but if you use like a k-nearest neighbor model as a classification scheme, K would be the number of neighbors it uses, and there's no real formula that I'm aware of that says, given your data, here's what K should be. So typically, I think of them as knobs on a wall, right? So you want to turn the knobs to get sort of some measurement in the green area, and the green would be getting good performance. So, you might try a 1 nearest neighbor model or a 7 nearest neighbor model and see how well those work. And then once you settle on that, that's the model you would use going forward. Maybe another example would be if anybody's ever used regression trees or classification trees, the depth of that tree is a parameter that can't analytically be estimated. There's no equation for that. And so what happens is when you fit typical trees, you build a very deep tree and then you use model tuning basically to find the right size that gives you the best trade-off between accuracy and overfitting. So basically what I'm trying to get to is a lot of the models I'll be talking about have these sort of structural parameters that we need to specify, and very often these structural parameters are the ones that control the complexity of the model. And so as the model gets more and more complex and more flexible, it has a more likelihood or risk of overfitting. And so by adjusting the tuning parameters very often is how you can underfit or overfit or get the model just right. So let's talk about like a nearest neighbor model. So what I have here is I have a plot. It's just a scatter plot. I have two predictors. There's A here on the x-axis, and there's B on the y-axis. And then you can see, if I look at the data points here, there's a fair correlation between these. I think it's about a 0.5 correlation. And then some of these data points are red circles, and some of them are blue squares, and those would be like my classes. So these might be like the poorly segmented, and these might be the well segmented. So when you go to predict a new sample, like this triangle, what a 5 nearest neighbor model does is it finds the 5 closest data points in the predictor space, and based on its classes, it uses those to predict this new sample. So I have 5 red circles that are closest to this triangle, so I'd predict this triangle to be a red circle. And then down here, as another example, I have mostly blue squares around here. So I would predict this one to be blue. So maybe if I had one that was more over here, if they were, let's say, 3 red circles and 2 blue squares, the majority would be red, so I'd classify it as that. And so that's kind of how a k-nearest neighbor model works, is it stores your training set, and then when you go to predict new samples, it says, okay, the most similar samples of my training set, what were they? And makes a judgment on that. And so, one nearest neighbor model has the most likelihood of overfitting the data because it's too attuned to the whatever very small local perturbations are in the data. But let's say you have a 100 nearest neighbor model, that might smooth out the information way too much. So in the case of k-nearest neighbors, when k is low, like around 1, you're worried about overfitting, but when k gets high, and I'm not sure what an appropriate value would be based on each data set, you worry about underfitting. So you're trying to find that area that's kind of just right in between the two. So what I'm going to do is I'm going to take these data and I'm going to fit one model, and I'm going to take the tuning parameter for that model, and in one panel of the data I'll show you what the model fit looks like for one tuning parameter value, and that tuning parameter I used using resampling. I'm going to show you how to do that in a minute. But in the other panel I kind of took that tuning parameter value and just boosted it up as high as I could make it. And so you can maybe see in 2 dimensions what that does to a model. So one of these overfits, right? So here's the same data as I showed you before. It's the same between the 2 panels. And in the class boundary here, everything on the south east side of this boundary, the black line, would be classified as a blue square, and everything else would be classified as a red circle. And you can see there's some red on this side and there's some blue on this side. It misses some, but it's a fairly smooth line, and it seems fairly reasonable. Model 2 is the other model where I sort of crank things up. You can see it's a little more responsive to the training set data, but the thing is, there's a little bit of blue here, so it's trying to find a really small island of blue here and a little island of red. So it's probably pretty unlikely, if we got another random sample of this data, that there's going to be a little finger, that comes out here and moves over here. So in this particular case, it really probably is overfitting along this boundary to little individual data points that are in this data set. There's probably not like a little mini island of blue that happens out here. And this is simulated data, so I know that's the case. Likewise, there's probably not a little tower of red that's sitting in the blue space here. So, this is overfitting and this is not. And the problem that we have is, in our segmentation data, we have 58-dimensional space for our predictors. We can't visually really assess overfitting. So we need some way to quantify whether a particular tuning value is good, in terms of being a nice generalizable pattern here that we're seeing, or whether we're overfitting. And so that's along the lines of what resampling does. Stop. Any questions? I'm assuming you guys can hear me okay, and I'm not just talking into the abyss. Okay. Continue. So what we'll do is we'll use resampling. So there's a lot of different forms of resampling. There's the bootstrap that a lot of the statisticians are familiar with, and then there's cross-validation. But every sort of flavor of resampling kind of, the ones I know of take sort of a similar strategy where you take your training set. So when you resample your data, you're only doing it on the training set. And you randomly take a subset of that data and use that to fit a model. And then what was left over, what you didn't use to fit the model, is what you make a prediction on. Okay, so you hold a little bit back from your training set, use the remainder to fit the model, and then that little bit you hold back, you make predictions on. And then you do that a bunch of times, let's say 30 or 10 or 50 times. And then you have a bunch of, let's say 30 or 10 or 50 estimates of performance. So every time you hold a little bit of data out, you calculate, let's say, the accuracy of the model or the root mean squared error. And so at the end of the resampling process, you have many estimates of performance. And it turns out that if you average those estimates of performance that were held out each time, you can get a pretty generalizable sense of how well a model did. Okay, so we'll talk more about cross-validation. Here's a little schematic I use in the book. So k-fold cross-validation, what it does is it randomly splits the data into k different groups that are about the same size. And then it takes k minus one of those groups and fits a model and predicts the one kth that was left out. So let's say k is equal to 3. And we would never use 3 for k, and I'll talk about that in a second. But let's say these data points here are randomly ordered. And on the first iteration of threefold cross-validation, we take 2/3 of the data and we build our model, and then we predict on the ones that were held out. And let's say we're doing classification, where we have a categorical outcome like we have in the segmentation data. We will get the accuracy of these 4 data points. But then on the next iteration of cross-validation, we put those back in, we take the middle third out, fit the model on these, and predict the ones that are left out. And then we keep going round robin. And so let's say the accuracy here, let's say it was more than 4 samples. On one resample, we might get an accuracy of 90%. In another situation, we might get an accuracy of 80%. And then maybe this one is accuracy of 87%. So we would take those holdout estimates of accuracy and average those. And that would give us a good sense of how well our model does. And the bright side about this is we don't ever have to use a training set for that. We can use we don't ever have to use a test set for that. We don't have to go to the test set until the very end. And so what resampling does is it gives us a good sense of model performance when we don't want to go to our test set just yet. So the thing about resampling is it's really like a lot of statistics boils down to variance and bias. And so the bootstrap has extremely good precision when it comes to estimating performance of a model, but it's really, really biased. Tenfold cross-validation is a pretty good way of doing it. You're only fitting 10 different models. And I should say, one common question I get is, we fit 3 different models here to our data in the schematic. What happened to those 3 models? And then the answer to that is we throw them out. The only reason we're using the models during cross-validation is to get estimates of performance. So we never really hold on to these 3 different models. They're only created to get a good resampling estimate. Okay, so but what I was going to say about cross-validation is k-fold cross-validation tends to have pretty good bias. So if the true model performance was, let's say, 80% accuracy, on average, cross-validation is aiming for 80% accuracy for the most part. The downside is it's extremely variable. And so, you might get 60 once, 100 another time. K-fold, or let's say tenfold cross-validation, it's fast because you're only fitting 10 models, but its precision is really kind of awful. So one thing that people typically do, and this is what I tend to recommend to people, is they do what's called repeated cross-validation. So if you do 5 repeats of tenfold cross-validation, you do tenfold cross-validation 5 times with different resamples, and then instead of having 10 of these accuracy estimates to average, you're averaging 50. And not to be the stereotypical statistician, but if somebody has something that's really variable, we tell them to measure it more, right, or to find a way to decrease the noise. And so what 5 repeats of tenfold cross-validation would do would be just to replicate that experiment so we can get good estimates, get better estimates of precision. And so that's what I tend to recommend for people. It depends on the data set size and a bunch of other factors, but that tends to be the approach that I recommend. It's what I'm going to use for the remainder of the notes. Okay, so sort of to recap here, what we'll use resampling for is to get good estimates of performance without using the test set. So kind of the big picture here is now we have a way to select our tuning parameters and really control overfitting. So let's say we go back to the k nearest neighbor model. We tend to use, when you have 2 classes, we tend to use odd values of k, so 1, 3, and 5, and 7, because we want to avoid ties. So let's say we want to come up with a candidate set of submodels. So let's say we want to test k equal 1, 3, 5, let's say all the way up to 25. And what we would do is for the k nearest neighbor model where k is equal to 1, we would resample that and get an estimate of its resampled, let's say, accuracy. And then once we have that, we go to the 3 nearest neighbor model, and then we resample that one. And so what we get over time is we get sort of a profile of resampled performance across a different tuning parameter. And so once we have that relationship between the tuning parameters and performance, then we can make sort of informed choices about what the value of the tuning parameter should be. So if we find that a 17 nearest neighbor model is really the optimal model based on resampling, then that's the one we would use. So we would refit the model on the entire training set with that one parameter estimate that came out of cross-validation. So our final model in the k nearest neighbor model might be a 17 neighbor model that used all the training set to actually build the model the final time. And that's the one you would perhaps go to your test set with. So again, the big picture is we're going to loop over a set of candidate parameters. For each one of those, we're going to resample them. And then at the very end, we're going to take that profile and find the optimal value. And the optimal value might be, pick the winner. Which one had the highest accuracy? There's a variety of ways to pick that one. But the final model used the entire training set and whatever the optimal tuning parameter was. So for the simulated data that I had up here, what I did is I did regular old tenfold cross-validation on that. And here's what the profile looks like. So when you had a 1 nearest neighbor model, the average of the 10 resampled estimates of performance is about 87%. When we went to 3 nearest neighbor model, we got a 2.5% boost in performance. The 5 nearest neighbor model went even further, and then it seems like maybe it stabilizes a bit over here. So this one here, the 15 neighbor model, might be the numerically best one, but I would argue anything between, let's say, 5 and 25 would probably work. And so then if we chose 15 nearest neighbor model, then that would be the one we would use going forward when you make any predictions on new data. The thing I want to maybe bring to your attention is if I look at the individual resampling profiles, this is the same profile. The scale is a little bit expanded because here are the individual resamples. So if this were like the first resample, you can see the pattern comes up, stays up a little bit, and then comes back down and wiggles a little bit. It might be hard to see, but here's another pattern here in this sort of orange where it starts low, it peaks at about a 9, or let's see, about a 7 nearest neighbor and 11 nearest neighbor model, and then it comes down. So there's a lot of noise here. This is the average profile, and this is a good illustration of how noisy tenfold cross-validation is. That sometimes it's estimating performance to be 95%, but for the same tuning parameter value, it's also in some instances estimating it to be a little more than 80%. So there's tremendous variation here in averaging things out. Especially if you can do more than 10 averages, can make a pretty big improvement on what your choice of your tuning parameter is. Okay, so that's sort of parameter tuning. So basically, you know, we know how, given this sort of algorithm, we know how to evaluate models. We know how to tune them. So once we know what their tuning parameter values are, we can take them and, you know, we can try something like, I'll talk about linear discriminant analysis in a few minutes. That has no tuning parameters. We can take a model like that, and we can fit other models like, you know, neural network or random forest and things like that. It's really advisable to fit a large number of models because some do very well and some don't. Predictive modeling is not this sort of situation where one model tends to rule everything. And you might pick the model that you're interested in based on, you know, a variety of different factors. You might need smoothness in the prediction equation. You might want to take the model that has the least number of predictors. So if the predictors are very time-consuming or very expensive to calculate, you might favor, let's say, a classification tree over logistic regression because it might use far fewer predictors. So, you know, performance matters a lot. That's what I've been trying to say about predictive models. But honestly, there are other considerations that can be made depending on how you're going to use them. All right, so that's a lot of talk without a lot of much R. Any other questions? So maybe get into R. So I took one or two models to illustrate this process. Linear discriminant analysis is a linear boundary model where the types of boundaries that fit here are not curved at all, they're lines. So it might try to fit a line here, maybe tries to split the diagonal here for the particular data. It's based on for your two classes, in our case, so the poorly segmented, well-segmented data. You get your vectors and means across the for that class. Do the same thing for the well-segmented data. It uses a common combination of your vectors. And then when you go to nodes here, it basically takes the dot product between your vectors and this plus one. And so if the discriminant function is greater than 0, you would predict it to be a poorly segmented sample. If this linear combination is less than 0, you predict it to be well segmented. That's a very simple model. Okay. Let's see. I'm not sure. I'll just keep going unless I should stop. So tell me if I should stop. All right, so the LDA function that I'll use is in the mass package. And there's a variety of ways to fit this model, even with the same function. So I'll talk a little bit more about this in a second. But I'm going to use a formula here, and I'm going to say in my segmentation training set, I'm going to model. I'm going to try to predict the class column as a function of all the other predictors. So I could have a list of predictors here, but the nice convenience here is this syntax means predict class based on all the other predictors that are in, or all the other columns that are in the model. And that fits in the linear discriminant analysis model. Now, I have a little extra parameter here. Some of the descriptors in this training set are highly correlated, and LDA thinks that they're linearly dependent, and they're not. And it will throw a warning unless you adjust the tolerance a little bit. So I didn't want to get the warning, so I adjusted the tolerance to be fairly low, and it wouldn't give me that particular problem. So, so once I get that model fit, there's a variety of different things I can do with it. I can make predictions with it. I can try to plot different aspects of the model. You know, I want to get straight to the prediction part, and so to get that, I would use the predict function and use it on that object, and I tell it what data to predict. So what I'm going to do is I'm going to predict the first, repredict the first three samples, the first three cells that are in that training set. And so when I get that, I get a list out of that. It has a predicted class, so the first cell would be predicted as well segmented, so would the second, the third one would be poorly segmented. then you can also get the class probabilities, the posterior probabilities. So for the first sample in the training set, the probability of being poorly segmented was about 26%, so that's why it's selected to be well segmented. The second sample was overwhelmingly predicted to be well segmented. Conversely, the third one was very highly predicted to be poorly segmented. And so this is how I would get my predictions. So let's say I want to estimate performance. You know, the first thing I could do is very simple, would be overall accuracy. You know, what's the percentage of my samples that I got are predicted correctly? You know, what's the percentage that I predict a well or a poorly segmented sample correctly? And that works fine. The problem with that is when you have a big class imbalance, you know, your baseline accuracy there is 95%, so it's really sensitive to class imbalances. Another statistic is kappa, which is sort of like a normalized measure of accuracy that takes into account the baseline event rate. And so you get your observed agreement, or your observed accuracy, and then based on the 2x2 table, you get your expected value, and then it normalizes by the expected value. So if you have a 5% event rate, you have a model that's 95% accurate, the kappa statistic would be about 0. So kappa is between -1 and 1. 1 means that you have perfect concordance. -1 means you have perfect anti-concordance. So -1 means you'll get them all right if you reverse the labels of what you did, which almost never happens. But 0 would basically mean there's no association between the predicted classes and the observed classes. So that's good if you have a class imbalance. I'll talk about the RC curve in a minute, and that's what I'll use. And that's really specific for two-class models. I'll get to that in about one slide. So another thing that people tend to use, another fancy name for cross-tabulation, is something called the confusion matrix. So the confusion matrix is just basically a table that shows the observed and predicted classes. You know, so you want everything to be on the diagonal where you get them predicted correctly, but you can then see what types of errors that people are making, how often they have false positives or false negatives. There's a bunch of different functions that do that. I kind of made this list a while back, and there's probably way more than there are on this page. We're going to use one that's in caret called confusion matrix. When we go to the RC curves, a lot of people use the rocker package. I tend to use the PRC package, so that's what I'm going to use, is the RC function in the PRC package. All right, so there's a question. Do we always have to evaluate many models, or do you have an idea what the best classification model is? Okay, so yeah, there's a lot of answers to that question. So there's this thing called the no free lunch theorem, which means in the absence of knowing anything specific about your data, no one model is any better than the other. So, you know, in general, I try to fit everything under the sun to data sets. And it's also the pre-processing matters a lot too. So, you know, you consider that part of the model. I've seen logistic regression beat the pants off of models that people love, like random forest. What I tend to do is I try to fit a couple of initial black box models, like a support vector machine or a random forest. And, you know, on average, those tend to give better performance. And so I can get maybe an estimate of what the ceiling is for accuracy. But then I'll try to fit models that are more simplistic, because that's probably what I want in the end. There was a paper in the Journal of Machine Learning Research last year, and what they did is they took, like, you know, dozens and dozens of models and fit them across dozens and dozens of data sets. And they found that, you know, the one that won most often was random forest, which is fine. Everybody loves random forest, and it's a great model. But, you know, it may be the winner overall, but I have plenty of instances where it does poorly against certain things. So, you know, that would be one of the ones I would try first, but I would almost never fit less than like 3 or 4 or 5 models in general. So hopefully that answers the question. What if the outcome is unbalanced? Yeah, there's a lot to say there. That's something that statistically we've ignored for a long time. We have a whole chapter on that in the book. Yeah, there's a lot of things you can do. I should also say maybe, so the Caret web page is on GitHub. Maybe let me open that up real quick. And the reason I bring that up is one approach for doing that is to do what's called subsampling. So if you have let's say a 10% event rate, what some people advocate doing is to take a random sample of 10% of your majority class. So you're only using 20% of your training data, but you're sort of rebalancing the training set, and that will sometimes help a lot. And the problem is that you know, a model like random forest optimizes on something. It's not accuracy, but it's relatively close. And so, you know, you can automatically get a 90% accuracy by calling everything the majority class in that instance. And so what often happens in the more flexible models is that they way more likely to overfit to the majority class. And so linear discriminant analysis, partial least squares, sometimes more simplistic models do better with imbalances because they don't have the power to sort of overfit. There's also these things called cost-sensitive methods, where you can place different costs on different types of errors. So if you want to push a model away from overfitting to the majority class, you can say the cost, let's say, of a false negative is 10 times more than the cost of a false positive. And in doing that, the models will try to like bend itself towards getting the majority or the minority class more often. So you know, I would say you know, you can look on the web page here. I'll talk about this package in a minute, but we tagged a bunch of different models, and one of those tags, let me enlarge this a little bit, is like cost-sensitive learning model. So if you do have an imbalance, you might think about using some of the models that are here. And so there are specific models. We highlight a lot of them in it's like chapter 17 maybe of the book, where it's all about class imbalances, how to measure performance with them, how to, you know, make your models fit better with those. Okay. All right. Let me jump back here. All right, so let's talk about an RC, or let's talk about maybe sensitivity and specificity. So when we have two classes, let's say the event that I want to predict, the event I'm most interested in are the poorly segmented samples, because those are the ones I want to get rid of when we're doing our data analysis. We can think about sensitivity and specificity, and those are sort of like class-specific accuracies. So sensitivity would kind of be the accuracy when we're talking about the event of interest. So I might take all my poorly segmented cells, ones I know are truly poorly segmented, and calculate the accuracy for those. And sensitivity is like the true positive rate. So if I have an event, a positive, what's the proportion of time that I get that right? And then sensitivity is the opposite of that, where what's the true negative rate. So if my specificity is 90%, that means that of the ones that are non-events, I predict them correctly 90% of the time. Okay. They're conditional probabilities. So if you're very Bayesian, you know, there's sort of the conditional probabilities are on the right-hand side, top of the fraction in Bayes rule. They don't take into account the prevalence or the prior probability of being an event. People use them a lot, and I have a whole rant about why that is. But it's what people tend to use in two-class systems. There's precision and recall, which are slightly different. I'm going to really mostly focus on sensitivity and specificity. The problem, one of the problems with sensitivity and specificity is you don't get, when you get predictions from a lot of these models, you more often than not get a probability of something being an event. And so you need to classify it based on some sort of cutoff to get sensitivity. So if I'm going to predict something to be an event, what typically happens is you say, well, if the probability of being an event is more than 50%, we'll call it an event. And so, you know, one of the downsides of sensitivity and specificity are that you need to know what that threshold is. Now, one other issue with class imbalances is that threshold could be very technical term, I guess, would be out of whack, where, you know, the 50% threshold doesn't really work that well when you have large class imbalances. And so sometimes you want to use something different, and that's kind of where the RC curve comes in. Right, so in Caret we have a function called sensitivity and specificity to calculate those two quantities. So the thing about the cutoff is let's say you take that cutoff and if the probability of being poorly segmented is greater than 50%, we'd label it as poorly segmented. So what would happen if we increase the probability cutoff? So if we say, okay, well, it has to be 75% now for me to call it a poorly segmented cell. So what would happen is you get fewer predicted events, fewer predicted positives, and what would happen would be, do I have this right? I think I have this wrong. If it's harder to call something a positive, typically your specificity goes up. So this is incorrect here because you have fewer positives, which means you have fewer false positives. But let's say we lower the barrier for something to become a positive. Let's say, okay, if the probability of it being a positive is greater than 20%, we'll call it a positive. Well, we're getting more things called positives, and some of them are positive. So our sensitivity in that case would go up, but many of them are probably false positives, so our specificity goes down. So what an RC curve does, and that stands for Receiver Operating Characteristic Curve, is it looks across many different possible cutoffs. And for each cutoff, it gets a sensitivity and specificity. And then what the curve actually is on the x-axis, it plots the specificity, or the 1 minus the specificity, which is the false positive rate. And on the y-axis, it plots the sensitivity, which is the true positive rate. And so what you can look at, here's an example. So if I have a 50%, for a particular data set, if I use the 50% cutoff, then I might get a specificity of about 86% and a sensitivity about 93%, okay? And I think this is for the red circle, blue square data set that was earlier. So what happens when I make it easier to become a positive? My sensitivity goes up. It goes from 93% to 97%. That's this point here on this curve. But my specificity goes down because I'm having more false positives. If I make it harder to be a positive and move the cutoff here to 0.8, then specificity goes up because there's fewer overall positives, but sensitivity goes down because I'm eliminating things that really are positives. And so each little bump in this line here is a different possible probability cutoff for my model. And when I'm over here is when the cutoff is basically 0, so everything gets called a positive. In that case, everything's their sensitivity is 100% because you're calling everything a positive, but your specificity is 0. And one notable thing is PRC package plots 1 minus the specificity here, but you can see on the axis it goes from 1 to 0. So that's why it says specificity instead of 1 minus specificity. So what's good about the RC curve is it's independent of that cutoff. So you can get a really good assessment of the model without having to worry about what an appropriate cutoff is. That's really nice. The way people usually capture or summarize this curve is to take the area of the curve. And so if each dimension here goes between 0 and 1, the best possible model you could have would be one that comes all the way up here to this point here, which has 100% sensitivity and 100% specificity. And if you hit that point up there, the area under the RC curve is going to be pretty close to 1. And so that would be the best case scenario. But if you have a model that was pretty much non-informative, it had no predictive ability at all, what would happen is this curve would kind of hug the line here of 50%. And so in that case, the area under the curve would be 0.5. So a really poorly fitting model would have an area under the curve of about 0.5 and look like along this axis. But a really good one would come all the way up here and have an area under the curve of about 1. I thought I had more messages. So one other nice thing about the RC curve is that it's really insensitive to class imbalance. So if you have a 5% event rate, accuracy gets kind of compromised by doing that because you're not sure, or it's hard to tell whether a 96% accuracy is really a lot better than a 95% accuracy. But the nice thing about the area under the RC curve is it's a good measure to use when you have big class imbalances because its capacity to measure model performance is not really compromised by the event rate. So that's a really nice thing. All right. Now that I've talked about it, let's actually make one in R. So just a reminder is I can get my predicted probabilities from LDA by using this syntax that's right here. And so what I'm going to do is I'm going to do that, but on the test set. So remember, my test set has about 1,000 cells in it. So I'm going to create an object here that has the classes and the probabilities. So when I load this package, I'm going to use the RC function. The first thing it needs is the actual true classes, and that's in the class designation. This is a factor that's either WS or PS. And then it needs a measure of likelihood. In this case, I'm going to use the posterior probability of it being a poorly segmented cell. Now, one thing that's inconsistent across different R packages is if you have a factor, what is it, the first factor that's really the event or the second factor? I tend to think it's the first factor, but some other packages and even things like GLM treat the second level of a factor as being the event of interest. And so in our case, the factor levels for this class variable are PS and then WS. So what I need to do is I need to tell what the levels are of my factor. The first one is going to be, what it wants to see is the first one to be WS, because the RC function treats the second factor level as being most important. In the way our data is arranged, it's the first. So that's what this little bit of code does here. And what this does is it calculates all those cutoffs and all the sensitivities and specificities across every possible combination in this test set. And then when you print that object out, it gives you the area under the curve. And you can see it's about 0.874. You can also plot it. And so I'll show the next slide where I use the plot function on this RC object. And to get the little dot to tell me where 0.5 is, there's an object, or there should be a comma here. There's an option called print.thresh, and that's there. That produces this plot. Let's see, you can see that here's probably about a 0.5, the 0.5 probability cutoff. So on my test set, my specificity would be about 72%. My sensitivity would be about 83% using the default cutoff. And again, the area under this curve was a 0.874. You know, one downside of the RC curve is it's hard for me to know just based on that area under the curve whether 0.874 is really good. Like if I have a 0.9 versus a 0.874, it's hard for me to tell what big of a difference that is. So it does kind of obfuscate some of the details of the curve. But overall, it's what I tend to use for two classes. All right. The other thing I can compute is the confusion matrix. So we use the function from the care package, and it needs the actual classes. Again, they're in the, I'm sorry, the actual classes are the reference here. So it's the class variable here, and then it needs the actual class predictions, the factors that come out of the LDA model. And then what it gives you is it gives you the cross tabulation. So there are 250 that we predicted to be well segmented that were not well, or that were well segmented. There were 96 that were well segmented that we predicted to be poorly segmented. And so what you can get is you get the various statistics here under the default cutoff. So here's accuracy, it's about 80%. Kappa is about 0.54, which is pretty decent. Here are the same numbers that you saw up above in the confusion matrix. 723 and 0.82, it was 7 up above here. So if you want to look at the predicted classes under the default cutoffs, that's how you would do it. No questions so far. All right, so here's the thing is there's a lot of inconsistency between modeling functions in R. If you know, one example would be how we specify the model. Another example would be, so like for example, we use the formula method with LDA, whereas there are other times we want to use the non-formula interface where we just give it a data frame of predictors and a vector of outcomes. These will give you the same model, but there are different ways to specify it, and there are some advantages using formula method and some disadvantages. The thing is, LDA has both of those, whereas something like RPart only has the formula method. So if you try to fit the model using sort of this syntax with RPart, it will throw an error because it doesn't have that syntax. So that it's kind of inconsistent between modeling packages and functions, which, you know, it's a little bit of a pain, but it's not that huge. Another example that's maybe a little more impactful is how we get for example, class probabilities. So if we use a linear discriminant analysis model, we get both the predicted classes and the class probabilities, without having to do anything. But let's say we fit a generalized linear model, let's say logistic regression, to our data. If we want the probabilities, we have to predict and say type equal response, and that'll give us the probabilities for the event of interest. But if we fit a boosted tree with the GBM package, the syntax is the same, but we have to tell it how many iterations of boosting, because it doesn't have a default. So you go to do GBM, you can kind of remember this, but then you forget to say how many trees to use, and so it throws an error. And then maybe you go to do a mixture discriminant analysis model in the MDA package, and it's not response, it's posterior. And then there's a lot of packages where, like our part, where to get the class probabilities it's prob, and other times it's probability, and other times it's even something odd like raw. And so it becomes a pain in the butt if you want to use different packages. You have to remember all this statistical minutia, and that's kind of a pain. And so what we did is we developed something called the CARET package, and what that is, it's CARET stands for classification and regression training, and what it is, it's sort of a unified interface that wraps a bunch of different models, and right now we're up to about 216 models. 112 was actually more than a year ago, so that's a typo. But what it does is it gives you a common interface. So in this particular instance, we settled on type equal prob, and then we make the translation that when you use a GLM model, it actually uses type equal response to the hood, but you only have to remember type equal to prob. Another thing it does is it streamlines all the resampling. So whether you're using bootstrapping or cross-validation, it kind of has a high-level interface to do that and do it across all the tuning parameter values. There's a bunch of helper functions, like the sensitivity and specificity functions that just weren't in R at the time we wrote this. And then also, one of the things about resampling is it's sort of embarrassingly parallel, that there's no real need to run these things in sequence. So if you have 10 cores on your machine and you do 10-fold cross-validation, you could theoretically run all those 10 models on different cores and make things run faster. And so we sort of have a unified interface to the parallel processing in R. So you don't have to run these things sequentially. You can get a lot of savings. It just had a 10-year anniversary last year. So when I first started working at Pfizer, I started working on this, and we put it on CRAN in 2007. We host it on GitHub. There's a JSS paper. We use it a lot in the book. So we'll talk about that a little bit. Okay, questions. And also, since I can't hear you, I know it's 10 after 8, and I'm running a little bit behind. You should flag me when you want me to stop talking. I won't be offended. I want you guys to go home on time. Let's see. So let me answer these questions. Are there options like RC for greater than 2 classes? There are. There are a couple different variants of RC curves that are multidimensional. I think there's another example of, or another paper, and again, this is all in the book and I don't remember the details, where you can do the one versus all RC curves. When you have, let's say, 3 classes, you can do the, one versus the other 2 and so on, and average those. I think there's some theoretical backup for doing that. So yeah, there are options like that. I haven't really used them all that much, but I know that they're out there. Deep learning, yeah, deep learning is great, it's great in specific instances that it's designed for. So I don't use it all that often because I don't have data sets with terabytes of data. So when you look at where deep learning is really being developed and where it's being used for a lot of image analysis, a lot of natural language processing, and it's extremely good in those instances. I've used it. I've tried it on those data sets. I've tried it on even relatively large data sets that I have. They're not very manageable. When you tune them, there are a lot of potential tuning parameters. They take a long time to run because they're so massive. I'm not saying they're bad. I'm just saying that they are really, really good under the context in which they're being developed. They're not bad under other contexts, but they're just not the tool. You can do you do just as well performance-wise with something that's much simpler to use. Again, I'll use random forest as an example. It's not my favorite classifier, but random forest is as low maintenance as you can get. It handles missing data. You don't have to worry about how, generally speaking, you don't have to worry about having a ton of predictors in the model. You can deal with class imbalances pretty well if you do a little bit of tweaking random forest. It's pretty low maintenance. In the times for the data sets that I've used deep learning, I get at least as good a performance as random forest without having to really do anything. And I'm kind of inherently lazy, so so there will be the instance where I need to use them, but I just haven't had that situation yet. So yeah. All right, so I use a test set here with LDA. I probably shouldn't have done that, because what I don't want to do is whenever I fit a model to use a test set. I want to, if I were doing this for real, I wouldn't go to the test set whenever I fit a model like I did here. I just wanted to do this for illustration. What I would want to do is resample our data on the training set and get a good estimate of performance. So when I did my test set estimate, I got an area under the curve of 0.874. So what I can use is I can use this train function that's in caret to resample the data set and get a resampling estimate of performance using LDA. So there's like 2 or 3 pages where I'm going to build up a fairly complicated function call, and I'm going to walk you through sort of each stage of doing that. So the first thing I'll do is I'll set the seed before I run train, and what that does is the first thing the train does is, if you haven't given it the specific resamples that you want to use, what it does is it figures out, based on the type of resampling that you want to use, which samples are held in and which are held out at every iteration. So if you want to fit 2 models and make sure that they use the same resamples, exactly the same resamples, you set the seed every time you call train right beforehand, and you'll make sure you get the same resamples. And so you have the formula and the non-formula method with train. So if I said X equal and then gave it a data frame of predictors and Y equal the classification variable, even if the underlying model that you want to fit only uses the formula method, it again makes that translation. So it allows you to use either the formula method or not the formula method, depending on what your preferences are. But the basic syntax is you tell it what you're modeling and where the data is, and then you tell it what method to use. So we're going to fit an LDA model, and so the method for LDA is a character string called LDA, which maybe isn't surprising. And so that's basically the minimum syntax you could use. But let's say the default resampling scheme uses the bootstrap, and so let's say I want to use repeats of tenfold cross-validation. And so what I can do is there's a control function that controls a lot of the sort of secondary aspects of the modeling. And when you use the control function, the method inside the control function is for the resampling. So if you say repeated CV, by default it does tenfold cross-validation. You can switch that to 5 or whatever fold you want. And if you tell it to do 5 repeats, it'll do 5 repeats of tenfold cross-validation. So then the only other change I make to my call is to say, hey, use this control function that I've come up with. And so that's tr control equals control. So then what would happen is, if I fit it at this point, by default it calculates the accuracy and the kappa score for classification models. So at the end of running this command, you would get the resampled accuracy estimates, which would be the mean of the 50 different holdouts that I did with the repeated cross-validation, and you get the resampled estimate of kappa, and that would tell you how well you did without going to the training set. But what I want to do is I want to get the area under the RC curve, and so I'm going to do a little more work here to make sure when it calculates performance for the model in the holdout set that it uses something besides accuracy. So what we're going to do is we're going to use this train control function again to pass in what I call the summary function, is the thing that summarizes the holdout samples. And so we need a function to compute the area under the RC curve. And let's say we want to compute the sensitivity and specificity based on the default 50% cutoff. Well, it turns out that we have one of those, surprisingly, because we do this a lot. And in caret, there's a function called toClassSummary. And if I gave it a data set where I have the class probabilities and the true classes, the output of that function is a vector that has the area under the RC curve, the sensitivity for the 50% cutoff, and the specificity for the 50% cutoff. And so this is the underlying function that I would use to calculate those. Okay, heard some clicks. So we need to tell train to use this function. So where that's going to come into play is we're going to say, hey, use the summary function called toClass summary. So it'll make sure it computes that on all the holdouts. The thing is, not all models have classification probability calculations, and so we don't automatically compute those. So one other little step here is you need to tell the train function to compute the class probabilities. And so another little step here is to say, yes, compute the class probabilities by setting this equal to true. Okay. Now two other aspects of this that I'll highlight is in some of the models, like the ones we'll talk about in a minute, they have tuning parameters, and you need to tell it, we're computing the sensitivity, specificity, and the RC curve. If you want to optimize any one of those values over a tuning parameter, you need to tell it which one to optimize. And so if I say metric equal to RC, you're telling it, hey, if you do have a tuning parameter optimize, pick the one with the highest RC curve is the way to pick the tuning parameter. That's not really what happens here because we don't have a tuning parameter for LDA. But if I don't put this in here, it'll give me a little message saying, hey, you didn't do this. One other really critical aspect of this is, these are all arguments to the train function that I've specified so far. We have the three dots or the ellipses that go from the train function to whatever underlying model that you're fitting. And so in this case, remember in LDA, since I have a high correlation between some of the predictors, it'll throw a warning saying that, hey, some of these things are linearly dependent. So this last little option here, tall, is not an option for the train function. It's an option for LDA. So if we go way back here, we fit LDA, we passed in this option, okay? And so what's nice about when you call train is any argument you give it that is not an argument to train gets passed to the underlying modeling function. And so that's really beneficial. We named as many of the arguments to train in sort of like non-standard ways. So TR control, we didn't want to call it control like every other package does, because if train had an option called control, then you couldn't pass a control option into the underlying modeling function. And so so you can do that kind of thing. You can pass things along to the underlying modeling function here, which is a nice little feature. So this is my call. So just to recap, what it's going to do is it's going to fit, let's see, we're doing 5 repeats of 10 full cross validations. So that's 50 different models. It'll use that to estimate the area under the RC curve for that LDA model. And then it'll fit a 51st model, which is an LDA model on all the training set samples. And that's the one that sort of gets embedded into the train object. So again, we'll use the first 50 model fits to estimate performance, but the very last one is based on the entire training set, and that's the one that will get used by the train function. Again, a little digression here. So parallel processing, we're fitting 50 different models here. We can break those up across different cores, like I mentioned. And so what we can do is we use the for each package, and for each is a way to parallelize for loops. And we use that under the hood in Caret. So if you don't want to do any parallel processing, you don't do anything extra, and you don't have to know how the state gets to your table. But if you do want to use parallel processing, the for each package works in conjunction with a bunch of other packages on CRAN. And those are usually named do and then some technology. So do MC is for multi-core parallel processing. That's on Unix and OS X. If you want to use Windows, there's another one called do parallel. And so so the way this works is you load one of these packages and sort of register that technology as being the parallel processing technology you want to use, and you can tell it how many cores to run or what the cluster's name is and all that sort of stuff. But you don't have to change any of your code for the train package. All you do is, if I use multi-core and I want to run it on 2 cores, I just load the doMC package and register doMC as the parallel processing technology, and then when it goes to do all the resampling, it'll split those 50 resamples across 2 different cores. And it's a linear speed up in the first couple of cores. So if you do 2 cores, you should get about a half reduction in the time it takes to execute things. If you do 10 cores, you're not going to get a 1/10 reduction. or the total times 1/10. But it never gets worse. But there is a lot of benefit to running in parallel. Yeah, heard some things here. Time series models including caret, not yet. So you can, I'm not going to go into this, you can write your own modeling functions to include in caret. So we have a whole part of the web page that's about, let's say you want to use some model that's not in our library. It's really not that hard to embed your own model into the train function. What we do have, and time series can mean a lot of different things. Okay, I'll answer this and then conclude. We do have some resampling methods that are very specific to time series. So yes, we can do that for some models. So some of the framework is there. Yeah. And then I think the last thing I want to show you guys is, maybe, assuming the battery's not dead, when we ran this resampling for LDA, the average of the 50 resamples is 0.8735 basically, which is as close as you can possibly get to the training set. So it did pretty well there. So we would have gotten basically the same answer without having to go to our test set. There's a lot more I won't go into. I'll just conclude. Here's an example of training a k-nearest neighbors model where it shows the tuning parameter profile for this particular segmentation data. So you can see each one of these dots here is the average of 50 resamples. So it would automatically pick the nearest neighbor that it liked and then use that going forward. There's a lot more functionality. Again, you have the slides. So you can either, I think if my email's not on there, you can always post a question on the website, or just Google me and you'll find my email. Okay, I'll conclude then, and thanks for showing up. And go ahead and drop me a line if you have any other questions.
See right now.